have to get undressed before you can give a talk these days. This is weird. This is almost a little bit too loud. Thank you. Anyway, so the purpose of the Quantum Gravity Institute will be to look at, in a sense, the four overlapping fields: quantum, gravity, technology, quantum, gravity, theory, and experiment. So most of you know me as a theorist. I'm going to be talking about experiment today, and primarily quantum, although there is some gravity that is mixed in with it. And in particular, what I want to talk about is analog measurements. Way back in 1980, thinking about Hawking's result, I came up with this idea of finding analog systems where one could test some of the ideas that had arisen. One of the most amazing things about physics and about, in fact, human endeavors in general is the fruitfulness of analogs, i.e., trying to understand one system by looking at other systems which are similar to that first system. The other systems are, of course, not identical, and as a result, they're not the same. So from an analog, you can never learn everything about the first system, but you can very often learn a lot. In particular, can one understand quantum particle creation, which certainly occurs in the overlap between quantum mechanics and gravity, by looking at other systems? The prime example of particle creation, if you will, is black hole evaporation, which Stephen Hawking discovered in 1974. As a theory, looking at the behavior of quantum fields, physics nowadays is all about fields, not about particles, even though we have whole sections in physics departments called particle physics. When you actually look at what the theorists do, they don't do particle physics, they do field theory. And if you look at the behavior of a field theory in the vicinity of a black hole, in particular a black hole which was formed by collapse, which as far as we know are all the black holes that exist in the universe, he discovered that the black holes, rather than being black, i.e. nothing coming out of them, were thermal, that they emitted thermal radiation constantly. Not just a little burst of it as the black hole formed, but forever after. Well, not quite forever after, because eventually the black hole would evaporate and disappear. For a solar mass black hole, that might be 10 to the 53rd times the age of the universe. So the temperature in that case was inversely proportional to the mass. For a solar mass black hole, that's about 10 to the minus 5 Kelvin. Very cold, so that's going to be very difficult to see anywhere out there because the universe itself is 3 degrees, which is 1,000,000 times hotter than this black hole would be. In addition, in 1976, while trying to understand Hawking's paper, I also showed that if you have a particle detector, that particle detector would respond, if you accelerated it, would respond with a temperature as though it were immersed in a thermal bath in a temperature of proportional to the acceleration. That proportionality factor is very, very small, so to get 1 degree Kelvin, you would have to have an acceleration of 10 to the 22, 1 followed by 22 zeros, an acceleration of that amount. So this is not an acceleration we will ever encounter in most of our daily lives. And this turned out to be extremely closely related to Hawking's discovery. Now, in 1971, I was asked to give a colloquium at Oxford. I was a postdoc of Roger Penrose's in Birkbeck College in London. And Dennis Schauma invited me to Oxford to give a colloquium, and I was trying to think of how to explain black holes to the people, because black holes were relatively recent phenomena at that time. And I came out with this analogy of a fish world in which we had fish physicists, and this world had a waterfall in it, and that waterfall was such that at a certain point here, the velocity of the water exceeded the velocity of sound in water. And one of the graduate student fish came a little bit too close to that surface and got swept over. And of course, he realized what was happening and yelled, "Help." The problem, of course, is that since the water is now flowing faster than the velocity of sound, any sound that he emits after he goes through that surface never gets out, because it's swept over faster than it can travel outwards. So as he's falling through that, the professor, this over here is the professor fish, all he's going to hear is something like, "Help!" And you'll never hear the end of the word. Well, this is exactly what happens in a black hole if you happen to fall into a black hole. As you're falling into the black hole, the light waves that you emit take longer and longer time to get out, and when you fall through what's called the horizon of the black hole, nothing else ever gets out. And so watching something falling into a black hole, you'll see it being redshifted instead of base shifted, as it would be in the case of sound, as it tries to get out. Well, this was a nice analogy, but then in about, I guess, 10 years later, I realized that this actually was a deeper analogy than I had thought at first. Namely, that one could actually start to do experiments, and if one looked at the mathematics of sound waves in a waterfall like this, that would actually behave exactly the same way as in Hawking's analysis of black holes. And those sound waves should also get created quantum mechanically and produce a thermal spectrum of radiation being given off by that horizon, that sonic horizon. So the analogy with a black hole was in fact much, much closer than one ever would have thought of at first. Ralph Schutzholder and I had suggested that instead of sound waves, one could also use the surface waves on water, and they would behave in exactly the same way, which led us, a group of us at UBC, led by my postdoc at the time, Silke Weinfurtner, to actually carry out an experiment in one of the long flume tanks in the civil engineering department that they used for teaching undergraduates about waves and so forth. And what we discovered, so this is, I like this drawing because it looks like a 19th century, from a 19th century textbook, the kind of drawing that you would get. This is a drawing of a flume tank where we have a pump which pumps water, a pump here which pumps water into this long tank that flows over this obstacle in such a way that the velocity of the fluid flowing over the obstacle is faster than the velocity of the surface waves of sound. And we could actually do an experiment to try and see some of the effects that one would expect in a black hole. And we published a paper on this, on the experimental results that we got. And this is sort of the key diagram from that paper. The solid line represents what the output would be if one had if the thing behaved thermally as Hawking would predict. And the little X's are what we measured in our experiment. And so we see that there's actually a very, very close analogy. This thing really does behave thermally. This is what's called stimulated emission rather than spontaneous emission. It's not what would happen just naturally if one left it, but Einstein taught us already in the 1919 that there's a very, very close relationship between stimulated and spontaneous emission. Then about another, 5 to 7 years later, Jeff Steinhauer in the Technion in Israel actually carried out experiments in Bose Einstein condensates. If one looked at that diagram that I had on the previous page, the temperature that one would have had in this water, these surface waves in water, was of the order of 10 to the minus 12 Kelvin, 1,000 billionth of a degree above absolute zero. So water, even in Vancouver, is a little bit warmer than that. And so one could never hope to see this spontaneous emission in water. However, in a Bose Einstein condensate, one can cool down a Bose Einstein condensate to temperatures like 10 to the minus 12 Kelvin. And that's what Jeff Steinhauer did. And he built a little waterfall by using the optical tweezers effect, namely that if you have light, if you have these atoms that make up the Bose Einstein condensate, and you shine light on that, and that light happens to have a frequency less than the frequency of the resonances in the atoms that one is using to build one's Bose Einstein condensate, then the Bose Einstein condensate gets attracted into that region of the light. And so this red sheet here is the light that we have, and the atoms in the Bose Einstein condensate get attracted in this region here into that and start to flow outwards. One sweeps the light with some velocity greater than the velocity of sound in the Bose Einstein condensate, and one builds up exactly the kind of horizon that I was talking about in 1980. And he did this and saw the quantum effects. This is the key diagram from that paper that he published. What this diagram here is, looks like a lot of noise, and most of it is a lot of noise, but you notice that there are these two wings, these two ears, if you will, designated by that green line, which corresponds to the correlations between particles or fluctuations in the Bose Einstein condensate, which are inside that horizon versus the ones that are outside. And if you look at that, you get a rather noisy diagram, but which is consistent with those ears corresponding to thermal emission from this horizon. And furthermore, he was able to argue that there's correlations between there's clearly correlations between what's going on inside and outside. That's what those ears are, is the measure of the correlation between inside and outside. And those turn out to be quantum correlations, i.e. these fluctuations, these particles, these sound waves, are what are called entangled, which is a purely quantum process between the inside and the outside of the Bose Einstein condensate. So one has effectively seen Hawking radiation, not from a black hole, because finding small enough black holes that they would actually produce the thermal radiation is extremely difficult. One would need a very small black hole in order to do that. Since we can't do it with black holes, we can do that with this analogous system, and we see that the analogous system is behaving exactly like Hawking predicted for black holes. Now, in that paper in 1976 that I published, one of the things that, as I mentioned before, that I showed was that if you had a particle detector, and what's a particle detector? Particle detector, quantum mechanically, is something which in my original was a little particle in a box. You could think of that as, for example, a charged particle held inside a little box. It has certain energy levels because of quantum mechanics. And when an electromagnetic wave comes along, in particular if a photon comes along, that photon will cause a transition from the lowest energy state of that particle in the box, so you start off in its lowest state, and kick it up into a higher energy level. That process of kicking it up into a higher energy level is precisely the detection of a photon in the electromagnetic field. If you just left the box sitting there, it would never get excited. If you were in the vacuum state, i.e. the state where you would usually say there are no photons, it would just sit there. It would always stay in its one ground state. But if there was a photon that came along and went through the box, it could excite that particle detector. If one now takes this particle detector, a simplified version was made by Bryce DeWitt, basically based on some work that Roy Glauber had done in the 1960s on particle detectors or photon detectors. One could think about a two-level system, one with only two possible energies, a lower energy and a higher energy, and look at what the probability is of exciting that, and regard that as a particle detector. If one took one of these particle detectors in the vacuum, i.e. you would usually say there are no photons around at all, you accelerate the particle detector, you would discover that the particle detector got excited. And it got excited exactly as though you had stuck that thing into a thermal bath of photons with a temperature proportional to the acceleration. So one of the questions is, can one use an analog system in order to see this effect? This is, in a sense, a primitive effect related to precisely related to Hawking radiation as well. But could one directly see this kind of effect? Well, there are lots of problems. First thing is constant acceleration in one direction would mean that very rapidly this detector was moving at the velocity of light, or in the case of sound waves, at the velocity of sound. And you would need an incredibly large detector and large experiment. For light waves, if you try to measure a temperature of, let's say, 10 to the minus 12 Kelvin for this acceleration, you would need something of the order of the size of the solar system, an accelerator of that kind of size, in order to see this effect. That's, of course, nobody's going to fund that. Furthermore, in these analogs, the effect depends, well, no, in general, this effect depends not only on the acceleration, but also on the fact that special relativity applies to the system. Now, for sound waves, special relativity, it looks a lot like light waves, but the detector doesn't act as special relativistic because the velocities are too small. What's absolutely crucial is the effect in special relativity of time dilation. In other words, of a rapidly moving object, the time ticked off by that object is much slower than, much less than it would be for an object at rest. That turns out to be an essential part of the effect, and that doesn't apply to sound waves. Furthermore, the velocity of sound is not a constant inside the velocity of sound is not independent of frequency for things like sound waves. For light, doesn't matter where you are, the velocity of light is the same at very high frequencies as it is at low frequencies. And as you accelerate this, the acceleration gets you up to velocities at which the velocity of light starts to change, or the velocity of sound starts to change. And that messes up the whole process. But fortunately, back in the mid-1980s, Bell and Linnaeus, that's J.S. Bell, who's the same guy who showed us some of the fundamental inconsistencies between quantum mechanics and classical mechanics, showed that if you have an object going in a circle, a detector going in a circle, it acts very similar to the effect that you would get if you had constant acceleration. Something going in a circle has constant acceleration as well. The problem is that the acceleration keeps changing in direction. As we know, when we whirl something around our head, we feel the tension in the rope. That tension in the rope is what's accelerating the object that's going in a circle around us, as Huygens already taught us 400 years ago. And what they showed was that that system also produced the same kind of effects. That you get a temperature there, it's now not the same as linear acceleration, because the temperature there depends on the frequency that the detector is sensitive to, but it only depends by a factor of about 20%. So this acceleration in a circle acts very similarly to the linear acceleration with a time-dependent temperature that gets developed. Now this makes things much, much simpler. There are certain difficulties. I mean, J.D. Jackson, for example, who had done some work on the behavior of particles in a cyclotron, back in the 1970s, never quite believed this relationship between temperature and the acceleration. And he pointed out that there are some strange features in the case that Bell and Linnaeus had looked at. There are some bumps and wiggles, as you can see down here, for example. And the asymmetry between this part of the curve and this part of the curve, that he said that can't be from any kind of thermal effect. And what I showed was that that came about because there are actually two thermometers for a charged particle whipping around in a storage ring, which is what Bell and Linnaeus were analyzing. There are in fact two thermometers there. One is the spin of the electron, which is what this calculation was looking at. In other words, in order to keep it going round in a circle, you have to put it into a magnetic field. That magnetic field polarizes the electron so that one spin direction has a higher energy than the other spin direction. So you could use that as a thermometer. But there's another thermometer, which is vertical oscillations of the electron as it goes around that ring, which can also act as a thermometer. And they're being excited by exactly the same electromagnetic field, and there's interferences between those two thermometers. And it's those interferences that explain these bumps and wiggles in the curve. Yes? Thank you. How do we measure in an analog system? So one of the things is, well, one of the problems with Bose Einstein condensates is that the way in which you make measurements there is you build the Bose Einstein condensate and then you smash the Bose Einstein condensate with light in order to look at the fluctuations, which destroys the Bose Einstein condensate. Jörg Schmidtmeyer came up to me in the hallway after a conference, and this illustrates the importance of getting together and having those conversations in the hallway, which for the past 3 years have been very difficult to do. He said, couldn't we use a laser to do this? And I said, sure. And it then took us another 2 years to actually make that sure into a sure. Do all the calculations, etc. So we developed a new kind of detector, namely, instead of dragging something through the Bose Einstein condensate, it was just a laser beam, a spot on the laser beam. We shine a laser beam through a Bose Einstein condensate. And that converts sound waves in the Bose Einstein condensate into photons in the laser beam. It acts like a microphone of converting sound waves into electromagnetism, which is what most microphones like this one, how they operate. And so we can measure at the same time a whole span of frequencies. The detectors I talked about had individual frequencies that they could look at, but they couldn't look at a whole span of frequencies. This detector can look at a whole span of frequencies. Let me, since I'm running out of time. This turned out to be extremely close to the way in which LIGO operates. Back in the mid-1970s, 1980, I did work on the quantum behavior of the detectors in LIGO, et cetera. And in particular, in LIGO, what you're doing is you're measuring the displacement of the mirrors, and as a gravity wave comes by, those mirrors at the ends of the interferometer move in opposite directions. And so LIGO is sensitive to opposite direction shifts in the laser beam traveling down the arms. That's exactly the same that happens in this Bose Einstein condensate. Only here the two arms are in frequency space rather than in real space. In other words, you split the incoming laser beam up into two separate frequencies, run those through the Bose Einstein condensate, and those two different frequencies act exactly like the two different arms in LIGO. And in particular, the noise development, what this allows one to do is to actually cancel out the effects of the laser on the Bose Einstein condensate, because these two frequencies are chosen in such a way that the effect cancels each other out. And the effect of sound waves in the Bose Einstein condensate produce opposite effects in these two laser beams. And when you bring them together, you get interference patterns that you can use in order to measure what the intensity was of the sound waves inside the Bose Einstein condensate. We wrote a paper on this a couple of years ago. Here's the kind of diagram. One has a laser beam coming in from the left. We run it through a modulator, which produces two beams at different frequencies. Those two beams at different frequencies are deflected, both of them along the same path. They go through the Bose Einstein condensate, and we have a little, if you will, a mirror here, which rotates these two beams around so that the spot on the Bose Einstein condensate goes in a circle, and that's acting exactly like this detector that's dragged through the Bose Einstein condensate in this little circle. So the modulator acts like the half-silvered mirror in LIGO. The two beams act like the two beams in LIGO, and they behave, the quantum mechanics behaves in the same way as the quantum mechanics does in LIGO. And so one can grab a lot of the knowledge that we've gained about LIGO in order to look at this kind of system. I don't have time to go through the details. There's some fascinating things in that. But the end result of our 2 years of work was that using reasonable parameters, and what I mean by reasonable parameters are parameters that people have actually seen in experiments, have actually used in experiments, not all of them at the same time, but there have been some experiments which have gotten down to that kind of accuracy for each one of the features of the system. And all we have to do is to bring them all together into one system. Of course, as any experimentalist will immediately tell you, bringing them all together into one system is far from a trivial task, but that's the task that we've set ourselves. And this is, being able to do this is a plot of the signal-to-noise ratio, and if a signal-to-noise ratio is bigger than 1, here's 1, this is a detectable process. And so using these reasonable values, we get a signal-to-noise ratio of about 4 or 5. So this should be detectable if we can only bring everything together, and that's what we're working on right now. So within the next year or two, we should get a good indication as to whether or not we can actually do this, and actually also see the acceleration temperature, which is closely related to the Hawking temperature, in an analog system. So watch this space. Well, no, I mean, in the waterfall analogy, for example, this, whatever the waterfall is, you know, if we think about a waterfall, it crashes down onto the rocks, etc. And so there's just a complete mess down there, which one could say is an analog of that central singularity of the black hole. But that information, of course, can't get out through the horizon.
Right. This is actually, I understand that it cannot get out of the horizon.
Right.
Singularity inside black hole is happening at one moment of time r equals 0. It is not actually the singularity is the center of the black hole, as you understand, because close to the singularity, the space-time is, okay, Kastner space-time.
Yes. So, I mean, one of the things about, I mean, people often ask, one of the things about this analog is that you don't have the analog of Einstein equations. So the equations that determine fluid flow are not Einstein's equations, and you can't massage them in such a way that they even sort of look like Einstein's equations. So any kind of back action effect, etc., just can't be looked at in this system. For example, one of the things that people often ask is, what about the entropy arguments for black holes? And one can't test the entropy arguments for black holes in the case of these analogs. They are just, that part of the analogy just doesn't go through. But that's actually important, because analogs always differ from the real thing. And seeing an effect which is independent of that difference also gives you insight into the phenomenon.
There is spatial overload, because there is another question also, because in the black hole, when it's evaporating,
right,
there is a negative flux of energy,
right,
which is going there, okay, and in this case,
right,
you don't have particles with negative energy with respect to the outside.
no, you No, you still do have negative energies, even in the case of the fluid flow. There is, if you look at it from outside, and if you define your energies from the outside, using, for example, the Killing vector, the fluid flow still has a symmetry. Use that in order to define your notion of energy. Then there are negative energies on the inside of the horizon as well, just as there are for black holes. So that part of the analogy is still fits here. It depends on what you call your energy. Right. Right. Okay. Yes.
So I have two questions. So one is you were too fast when you discussed belts inside that
right,
circular acceleration or periodic acceleration also would do the job. Did you show experiments there? So is there any, or was this just a simulation? So is there already some experimental signature from accelerators?
So the proposal that they made was that you could use, for example, Hera, the used to be storage ring, electron storage ring, in order to test this. One of the problems is, of course, that there are all kinds of other fluctuations in the magnetic fields in the storage ring, which could also produce spin flips. So it's not clear to me that the experiment ever got carried out in that system. There was a worry that people had, and this is why J.D. Jackson was working on it. They discovered that they could never get 100% polarization of the beams. And the reason is because the beam, as it's accelerating, sees this thermal flux. And that thermal flux excites the beam and means that you no longer have 100% polarization. So there's a direct consequence. The problem with electrons is that it turns out the same magnetic field accelerates them as splits the energy gap. And so the energy gap and the acceleration are tied to each other for electrons. And it's basically the G factor of the electron. And that G factor of the electron, of course, we can't change. It's given to us by God as 2.01, blah, blah, blah. So if we could get materials in which we could change the G factor, then one could carry out an experiment in a storage ring. But we don't have those. But in these analogs, that's easy to do.
And the second one,
The microphone.
Hello.
Yeah.
okay. And the second one is in your proposal with Jörg and Silke. What is the signature in the end that you? The analogy with LIGO is beautiful. So it's in a sort of
what
interference.
The signature is you recombine those two frequencies on a detector.
Right.
Interfere. You look at a certain frequency band of that interference on the detector, and what you see is excess noise.
Okay.
And
so
the whole process is set up just as in LIGO. LIGO is set up so that you're looking at the dark port because that cancels out the noise that comes from the laser beam itself. Similarly, in this case, one is effectively looking at the dark port and the noise from the laser beam itself gets canceled out in what you're looking at.
This I understand. So I guess then you would also see then the statistics in the noise.
Right.
Okay. I see.
So you look at the shot noise statistics and you find that you get excess, if you will, excess shot noise coming in the detector, which is what thermal noise is just excess noise.
Right.
Okay, I better let the next person.
Yes, right. So I think let's thank Bill again